Hey guys, it's the Techie Biochemist here, coming at you with another tutorial. Last time we covered how to follow the NAMD tutorial to do a simulation of ubiquitin in a water sphere. Today I'm going to show you how to do the same with a protein of your choice downloaded from RSC PDB. So from start to finish, let's get into it. For starters, just in case you're not already familiar with RSC PBD, that is where you can get PDB files. The Protein Data Bank has probably at this point millions of proteins contributed by scientists all over the world and free to use. In this case, I've selected the protein 4-hiridin. This is originally an NMR, I believe. Yeah. So here's the file I chose. To get it, you hit download files and you're going to hit PDB format. What the heck is this thing? Hiridin is a protein used by medical leeches. That's that organism, Hirudo medicinalis. That's a medical leech. They're pretty cool, and those proteins are super useful in helping skin grafts take and lots of other cool science, so that's why I'm exploring it today. So I actually already downloaded it and I put it in my PDB folder here under VMD. And that is where we are going to start. Even though this is a NAMD simulation, we have to start with VMD to actually prep that PDB file for the simulation. So the way we're going to do that is go in here under PDB, find 4-hiridin, load her up. And there she is. I'm going to minimize that and get it out of our way. But yeah, with the line form, we can see that kind of basic thing. I'm going to change the graphics over just so we can get a slightly better look at it. I'm going to go to new cartoon. Excuse me. And there we go. Pretty simple, small protein. But that's good because the larger a protein is, the longer it's going to take to run a simulation and the more strain it would be on my computer. So we'll start with this little guy just to run through and show from start to finish what a clean run of this would look like. First thing we're going to do is we are going to build a PSF with the automatic PSF builder. We're going to come through here and delete all of these charm files out because we want to use specifically the NAMD one. So I'm going to go to Documents, NAMD Tutorial, and in 1.1 build, there's this topology, all27 protein.imp. That topology file is going to be great for actually building this thing. I'm going to set this to protein because if there's any water molecules or anything like that, I don't really want them involved. I want to keep this simple. Hit create chains and finally apply patches and finish. Those files are created now. I'm going to delete this out. And also delete this actually. And then I'm going to load in the auto PSF and PDB first, and then on top of that load in the auto PSF file. Important thing to check here is I want to make sure that on this line structure there's no lines branching off to nowhere. That would be concerning if there were, and there's not. All right, let's just keep working with this thing. So now that we have the PSF and PDB, the next step is another modeling. We're going to add a salvation box. So in this case, we're just going to make sure that this reads what we want it to. Yep, auto PSF. Okay, looks like that's already set up for us. For down here, if we use molecule dimensions, we don't have to worry about box size. So really the only thing we need to do is worry about min and max padding. In this case, we're going to set minimum to -1 and maximum to 1. That's just going to kind of keep the box centered. And then we're going to hit Solvate. And you might not immediately be able to see here because it's a little unclear, but basically that protein is now surrounded by water. I can show this a little bit better if I change around the representation, so let me do that real quick. All right, by reducing the sphere size so we can actually see what we're looking at, can now see that this protein is surrounded by water molecules in a box. And so this is basically going to become our water sphere. The final thing we need to do here before we exit VMD is I want to come over to TK console and say set here atom select top, I'll just say all. Oh, shouldn't have the $sign in there this early. There we go. And now I'm going to say measure center here. And there we go. I find that the center is basically 1, 1, 1. This one's closer to 2, so I'll say 1, -1, 2. And with that, we are done. Now the files that I've created are the solvate PSF, solvate PDB, and the auto PSFs. The auto PSFs I can go ahead and delete. They're not really important at this point. Actually, I'll undo that. I'll keep the PDB and the PSF in case I need to regenerate the solvate for any reason, but I am going to rename this solve for here. Solve underscore for here. PSF. And those are just going, that way I know exactly what those files are. The last step that I need to take before I actually jump into running the NAMD simulation is I'm going to open up PyMol. So I'm just going to navigate to and open that solvate PDB that I just created. And here we go. The final thing that I'm going to do here, now that I've got this in PyMol, is I'm going to do a measurement from corner to corner using the measurement wizard. Up here under wizard, I go down to measurement, and it tells me please click on the first atom. So I'm going to select an atom at that corner, and then I'm going to select an atom on the opposite end. And that number it gives me is 40. So that's like the absolute maximum number that that these water molecules essentially can be away. If I half that, it's like 20 for each of them. So I can probably put a spherical boundary at roughly 20, we'll say 25 angstroms from the center. Could even be a little generous and say 30 there. So that's what we'll do. We'll say spherical radius of 30 angstroms. So now that I have all of that information, I am ready to go ahead and jump into the actual NAMD tutorial portion of this video. So under NAMD tutorial, the first thing we're going to do is we're going to come into 1,2 sphere, and we're going to copy the configuration file for the ubiquitin water sphere equilibration. We're just going to copy it over in, or duplicate it into the NAMD tutorial folder, and I'm going to rename it for here water sphere configuration. It jumps up here with that new name. So let's go ahead and open it up, and I'll show you how to configure this for this particular protein. So first thing is, of course, this is still trying to reference the ubiquitin files in the common folder, assuming that the configuration file is located in 1,2 sphere. Okay, so not only is this file no longer located in the 1-2 sphere folder, it's now located in the NAMD tutorial folder, but also these files aren't the ones we want to reference. Instead, we're going to come over here to VMD, and we're going to move the solvated for Hiriden over into our NAMD tutorial folder. So those are the files we're going to be referencing, and therefore I'm going to change these to represent that. So I'm going to just say, I don't have to have a / anymore. I can just say solve for here.psf and solve _ for here.pdb. I'm also going to change my output name to for here water sphere equilibration instead of ubiquitin. And I'm going to change that temperature from 310 to 280. I think that's just fine temperature in Kelvin for this. Finally, I am going to use the same parameter file. However, since I'm no longer in a lower folder, I'm going to remove one of those dots so it's not going to go up to folder levels and then go looking for common, because common is in this folder now. And now I need to actually adjust the spherical boundary conditions. This is important because these numbers are all set based on the assumption that it's working with that ubiquitin protein, which isn't the case. So for spherical boundary control settings, remember how we checked where the center is of the protein in VMD? Well, we made sure it's at 0, so now we're just going to type in 0, 0, 0 because that's basically where the center is. This is the radius, I believe, essentially, of the of that spherical boundary, and we said, I think we said like 30 is enough. These refer to kind of the strength of the force that will pull back on any atoms that escape that radius, and that'll be fine. Finally, I am going to increase the minimization steps to 200 just so that there's a little bit more time to make sure that everything's kind of squeezed in before the simulation starts running. The other thing I need to come up here and adjust is the MSM. I want the MSM to be larger than the spherical boundary by a factor of 5 to 10. I'm going to just say 10 and then set these MSM boundaries to 40 in every direction. That should be good. So let's go ahead and run it. Same thing that we did with last time's ubiquitin tutorial. We're going to say cd NAMD tutorial, and then I'm just going to say /NAMD2 for here _ws configuration greater than sign, and I want to write all of this in a log, so we'll say for here water sphere eq.log, and finally an ampersand, and then I'm ready to hit enter. And this is probably going to run for a minute, but there shouldn't be any errors, so I'll open this back up when it's all done. All right, guys, and I'm back. We are done. As you can see here, I've got a done message, and if I can't double check that by opening up my log file, and there we go, at the end it says end of program, telling me that it's done. I now have a DCD file. So I'm going to open up VMD again and just kind of check my results. Since I only ran it for 500 steps, I'm probably only going to have like 2 frames, but still, that should be pretty good to at least get a rough idea of kind of what's going on here. So we're going to go into Documents, NAMD Tutorial, and I'm going to open up first the PDB, then the PSF, and finally that brand new DCD file. And sure enough, yeah, there's only 2 frames. So not a whole lot going on, but you can see that at least it worked. And I would be able to run a much longer simulation with these settings and get it to work nicely. In the meantime, you know, just to kind of give you a better idea of what's going on here. If I put it into surface and tell it just protein, you can see just a little protein wiggling across its 2 or 3 frames. So there you go. Now you know how to run from start to finish your own NAMD simulation of a water sphere equilibration on a protein of your choice. Next, let's go into some common errors that you may run into when you're trying to do this and how you would solve those. So if I open up this configuration file, the first thing would be here if I put 2 dots instead of 1. Essentially, this is going to be completely relative to where you have your parameter files and everything located. In this case, of course, that parameter file is in the common folder. You might be able to already identify what the problem is. This configuration file is in the NAMD tutorial folder. This first dot is telling it to look in the NAMD tutorial folder. That second dot is telling it to go up a level, which would be documents, and then look for a folder called common. Obviously, there's not going to be a folder called common in my documents level, so that is going to result in an error where my computer is going to tell me can't find that parameter file. So let me demonstrate that real quick. cd NAMD tutorial /NAMD for HIR underscore water sphere dot configuration. And I'm not even going to bother with a log file. I'm just going to have it run in my terminal because I know. Okay, no such file directory NAMD. That's because I need to add in NAMD2 here. If I run it now, fatal error, unable to open charm parameter file. Like I said, completely expectable because I didn't put the correct path to that file. Next, I'm going to correct that so it looks in the right place. But I'm going to change and misspell the PSF file to solve instead of solve. So if I run this again, now it's going to say unable to open the file. And that's because, again, as far as the computer is concerned, it doesn't exist. Why does it say unable to open instead of unable to locate? Impossible to say, but that's what's going on there. So if I change that back, now it'll run clearly. Now let's discuss some of the actual configuration settings based errors you might get. One would be if your spherical boundaries aren't set right. So if I were to set my spherical boundary to only say 5, and I'll reduce that to 100. If I try to run this, what's going to happen is it is going to start running, and it'll even probably go through the minimization steps. But then as soon as it hits the actual run step, it's going to probably throw me rattle errors. So let's see here, small bc log. I am using a log file on this one because it is going to be way too much to just keep up with. It's going to take a sec to get through all these minimization steps, so we'll just hold on for a minute. If I now go to the bottom of this file, you can see as soon as we got to the end, to step 100, which was the last minimization step, and it reinitialized velocities and tried to run, we immediately hit a rattle algorithm failure for one of the atoms. Essentially, that's just because the boundary was too small. At 5, that is way too small. We needed it 30. So setting it back to that, this should run well again, but this time I'm going to screw around with the MSM grid. So the MSM grid won't necessarily throw an immediate error as soon as you get to the end of the minimization steps. And in fact, the more minimization steps you use, the more you're able to potentially overpower a MSM grid that is too small. The turnaround, though, is that eventually one of those atoms, no matter how much you minimized it, eventually one of those atoms is going to jump out of the spherical boundary bound. And if your MSM is even smaller than that, that means that it's going to jump outside of the MSM grid, and that's going to throw an error too. So let's see what that does. This time we're going to say small MSM log. And just to make sure this actually happens, I'm going to set the run to actually 1,000 instead. The important thing here is that the spherical boundary is smaller than the MSM grid in all directions. So actually, you know what, I'll make it 1,500. I'll make it 2,000. We want to make sure we hit that error. And with these settings, eventually we will. This time it actually didn't throw that error. That happens occasionally. Basically, this thing just occasionally you don't run into those errors. So if we open it up, the log that is, it did happen, but it only happened at the very last step, so it's fine. But you can see that is the error that you had, and if it was trying to continue on past this point, it would have just died. As it is, we probably did get a full simulation run. But just to make a point here, I'm going to further reduce this MSM to only 10, and we should hit that error a lot sooner than 2,000 steps. Let's do it again, and we'll see how long it takes. Again, the minimization step should run cleanly. You should never hit an MSM error really until after the, oh, that's the old one. I want the new one. You shouldn't hit an MSM error until after the minimization, and here we go. Yeah, there were 100 minimization steps. It didn't hit it immediately. It got to 200 steps, and then at 300 steps, there we go, fatal error. So as you can see, the smaller the MSM grid is, the more likely you are to hit that error, and the quicker it's going to happen, or is likely to at least. The two ways you can kind of work around that is by just increasing the MSM grid. You want it to be like 5 to 10 angstroms larger in all directions than the spherical boundary control radius. The other thing is that you can potentially further delay potential MSM errors by increasing the number of minimization steps. If I were to increase these minimization steps to say 500, we're probably going to get, even if we keep the MSM at 10, we'll probably get to closer to like 500 or 1,000 steps in. So I'm just going to show that. Like, this is just kind of a probabilities game, so there's no guarantee of it, but I'm going to bet that we are going to get more than 200 actual steps in, because that's essentially what we hit last time. The first 100 steps were minimization, and then it basically did 200 actual steps of running before it hit the atom outside of grid error. This time, I'm willing to bet we'll make it to more like probably 700 steps total. Yep, there we go. I said 700, it made it to 750. Pretty good. So yeah, that's kind of some of those errors, and hopefully that helps you troubleshoot and know how to fix them. I wish you best of luck in your endeavors. Drop me a comment if you run into an error I didn't cover, or if you hit some in the VMD stages, and I'll see what I can do to help you out. Hope you enjoyed this video. Give it a thumbs up and subscribe so that you know when I post more videos to help.